Hello ladies and gentlemen, good to see you again. Thanks for tuning in today for the 8th laboratory session that we're doing in GGS 300, so Quantitative Methods for Spatial Science. I hope that you've been able to have a look at the previous lecture where I covered the high-level theoretical approach and for ANOVA, analysis of variance, and we covered both the parametric ANOVA test and also the Kruskal-Wallis non-parametric test. And what we're going to be doing today as a consequence is actually working out how to calculate those specific tests, and we're going to be working through in the R code to actually produce the test statistic and the p-values for different data sets that we have based on the math that we went over within the actual lecture. Okay, so I hope that you're able to spin up your RStudio, download the code that should be online from the MyMason portal, put it in a folder, spin it up from there. You shouldn't need any external data today, it's all going to be loaded in, and we're going to start by carrying out an analysis of variance tests just on some basic sample data that we've just created here, but it takes inspiration from the 3 or more samples example, which is in McGrew et al. On page 181, which focuses on house price data. So imagine that we have these 4 different samples just here, and essentially these are all house price data points that we've taken from various different places. So it's a sampling exercise, and what we want to do first is just load these data into the global environment for RStudio. So we've done that here. Now we've got all of them, all of the vectors within the global environment, and we're able to start to basically piece them together so that we're able to obtain a data frame. So what we did initially was load them all in as separate objects. This just stitches them together basically into a single vector, and then we're able to allocate groups to each of these based on the number of samples in each. So when we stitch them together and look at the data frame that we produce from the price and the group variable, we basically end up with a group variable here depending on the sample that it's come from. So these are all the prices for group 1, so sample 1. Then we've got the prices for group 2 just here from row 7 down to 13, group 3 from 14 down to 18, and group 4 from 19 down to row 22. Okay, so I hope that that's fairly straightforward to you now. So basically how we kind of load in a set of data, how we then are able to stitch together a bunch of vectors that are in the memory. So we've used this .dataframe function before, so I hope it won't be too alien to you. But it's useful to be able to manually create these data frame objects so that you can you import your own data here like this, or you can also produce reproducible examples. If you are stuck on a problem and you need to post it on Stack Exchange, you need to be able to show how to generate something fairly simple like this. So those first couple of lines of code just produce this one data frame 1 object that we basically want, which contains all of our data. Now you remember when we actually were covering in the lecture the materials, one of the things that we did before we started looking at the tests was actually to visualize the descriptive statistics for all the different sample groups that we've got. So down here we had the high school graduation rates for states within the northeast, the south, the north central, and the western areas of the United States. And we were able to show the box plots and also the notched box plots, as you can see over here, which are kind of broadly equivalent to a 95% confidence interval. So this can give us some sort of indicative visualization to suggest whether the samples come from the same population or not, depending on whether there's overlap or not. So let's just have a go at trying to hack through that data and produce some of those plots that we're interested in so that we know how to do this for the future. So I'm using the box plot function here, which if you take a look in your memory, you can see produces a box and whisker plot of the given group values. And actually there's quite a lot of arguments that you could use here. So you could provide labels, you could drop certain variables, maybe if you've got missing data. You can specify lots of different things for how you generate this particular visualization tool, which is pretty powerful, to be honest. I do like a good box plot. So let's just plot it here, and you can see that we've actually plotted the price on the y-axis, and we've got the 4 different samples here, which are categories basically along the x-axis. So sample 1, sample 2, sample 3, sample 4, and we can see that there's quite a bit of difference between them. So that's one way that we can generate a box plot. We can also generate it by using the actual data frame. So here we took the individual samples, and we basically gave the function all the individual samples, or here we can just use the vectors that we've got, and it's going to produce the same thing. So they're the box plots. It doesn't give you the notched box plot approach. So what I'm doing here is just giving you 2 more functions using the same box plot approach. Again, the first time I'm giving the different samples to the function, the second time I'm giving it the vectors. But either way, I'm basically saying notch equals true. So you'll remember that we had lots of different arguments in the help menu. Here we go. And if you go in the help menu and you look for notch, here we go. If the notch is true, a notch is drawn in each side of the boxes. If the notches of 2 plots do not overlap, this is strong evidence that the 2 medians differ based on Chambers et al. 1983, page 62. So that's a pretty handy feature to have. Let's run that now and take a look at it. So here we have the notches for all of the different groups, and we can generate in 2 different ways. And we're already starting to see that there isn't necessarily overlap or full overlap between the distribution of each of these categories. So that's indicative that the samples may have come from different populations. Okay, so I hope that that's clear to you now. You're able to generate those nice looking plots. Let's move on to actually generating the underlying data and carrying out an actual analysis of variance test. So you can look at this in combination with the slides which I produced in the lecture. So you remember that there's 3 steps, which basically consists of about 6 different individual parts. So we have 3 for calculating the between group variability, 2 for calculating the within group variability, and then finally we need to calculate the test statistic. So what we're doing here for each of the samples that we have, we're first interested in getting n, so the number of samples. We're then interested in taking the mean, so that's the x bar, the sample mean for that particular group of data points. And then finally we're interested in getting the variance, so we get the standard deviation here, so the standard deviation of the sample. And when we load those in, we get M1, X1, S1, and then we're able to do that for each of the neighborhoods sequentially. So we get all of the necessary statistics for each of those samples for us to move ahead with the analysis of variance. Here we go. So now we've got N. We've got the X bar means of the sample. And we've also taken the standard deviation, so we've got the variance for the sample as well. So let's move on to step 1. So this is for calculating the between group variability. And in part 1 we need to calculate the total weighted mean of all samples. So we're looking at this equation just here. What we want to get is x bar t. And what we need to do to calculate that is we need the mean of samples. We need the number of observations in each sample, total number of observations in all samples. So what we're doing here is we're basically getting a vector of all of the sample lengths, so the number of observations for all of the So we're getting the sample length, so we're getting the number of observations for each one of the samples that we've got, all n, and then we're also doing the same. We're basically creating a vector of all of the sample means, so that we've got that all in one particular place. We also need to get n, which is the sum of all of the observations across all of the samples that we have. So let's see what that value is here. So that's 22 for the number of data points that we had for these first 4 samples. And what we want to do therefore is get the x bar t. So essentially what we need to do is we need to sum all of the number of samples that we've got across the 4, and we simultaneously, sorry, I'm on the wrong line here. What we need to do is we need to sum all of the multiplication of the number of the samples and the sample means. So you see here, sum all n times all x divided by the number of observations in the sample. So that should provide us here with the x bar t, which is essentially what we're going to carry forward into part 2 just down here. So let's run that now. We're able to produce the x bar t, and that's gone into the global environment for R. Now in part 2, we're going to focus on getting the SSB value, so the between group sum of squares. So what we need to do is we need to basically sum, we need to square the sum of the squares. So how do we do that? First, well, we need to take the x bar t from all of the means that we've got in all x. And then we basically we square them, multiply them by all of the samples that we've got, and we take the sum of that. And when we do that, in this particular case, we end up with 6,769.394. So that was for this particular calculation just here to get the SSB. We need to sum through the data in order to produce that metric. And we're able to enter that into the global environment now so that it's saved. We can see that number's just arrived here. So for part 3, we then need to basically estimate k, so that's the length of all of the number of samples that we have. So let's take k. So we've got 4 different samples for the length of the all n vector. So they were the 4 house price samples that we'd taken and inputted into the memory just up here. We need to take forward the SSB metric that we generated in part 2, and then we basically need to divide it by the number of degrees of freedom that we have as the denominator down here in this calculation. And when we do that, we get an answer of about 2,256.465, but the important thing is actually assigning that to the MSB metric so that we've got the between group means squared. Now that's in the global memory up here. So basically that means that we've got the numerator for the first part of that calculation for how we then calculate the test statistic f. What we don't yet have, as you'll see there, is we don't have the MSW, so basically the within group variability. What we're really after is the within group mean squared. So in order to do that, we need to move on to step 2. So once we're on step 2 in part 1, what we're going to do is going to create a vector which basically contains all of the standard deviation values for those 4 samples. So you can see here we've now entered all S, so all of the standard deviation values into this vector, which are just here. And then we're able to take that forward into the calculation, which will allow us to actually generate SSW. So essentially what we want to do is we want to obtain this value here. And we're going to need to do that by subtracting 1 from all of the number of observations in each sample. So you'll remember that that's essentially the number of degrees of freedom. And then what we're going to need to do is multiply it by all S, so all of the variance values that we have, so the standard deviations. And we square them and then sum them, and that gives us the value that we're after for the within group sum of squares, essentially. Then we need to move on to part 2. So now we've got that value that we were after, so the SSW here, and we're able to basically then use that as the numerator and divide it by the number of degrees of freedom that we have in order to obtain the within group mean squares. Okay, so what we're going to do is going to take the number of observations, subtract k, which is the number of group samples, so that's 4 in this instance, and the number of overall samples that we have is 22. We already covered that, so you can see 22 just here, and k, which is 4. So then when we do that, what we're doing basically is we're getting 344 as the denominator for the calculation for the test statistic. And that basically completes step 2, which was necessary to get the within group variability. So finally, let's finish now on step 3. So we have to take forward the MSB and MSW values and divide them in order to get the F statistic. And you're seeing that we're getting an F value about 6.55803. So what we then need to do is we need to give that, we basically need to give that to the R quantile function. So let me just show you here, help PF, which enables us to use the F distribution, and we want to be able to give it a quantile value and basically get a p-value returned from that. So what we're doing here is we're giving it the F statistic, we're giving it the number of degrees of, sorry, this is the number of degrees of freedom that we have. Oh, sorry, we have the number of degrees of freedom for the we have the number of degrees of freedom for data frame 1 and the number of degrees of freedom for data frame 2. So data frame 1, we have the total number of samples, and then for data frame 2 we have the total number of observations across all of the samples, and that's how we end up inputting 3 and 18 here into PF. But the important thing when we do that is that we get a p-value, and for those astute members watching this, you'll see that that's very, very low, so it's highly significant, far below the 0.05 alpha significance level which we've used previously. So based on the information that we've got here at the 95% significance level, we would be confident that we could reject the null hypothesis, and that would basically mean that the samples that we've got, which we tested, have come from at least 2 different populations. Okay, so the samples are significantly different from each other, and that variability, that difference is larger than what we would just expect to occur by random through normal random sampling. So let's test those results that we got, and there's multiple different ways that we can do that. Okay, so if you just have a look at the function here, so oneway.test, you're able to test whether 2 or more samples from normal distributions have the same means. So if we do that for the price data and the group, and we tell it the data that we want to use, we produce an F statistic of about 6.558, and we end up with a p-value of about 0.003449, so very, very much the same as what we were able to achieve just by manually working through those calculations. So that's one particular way that you can calculate it. I've given you 2 other ways in which you would be able to calculate this. So for example, if we just look at the help menu here for AOV, this allows us to fit an analysis of variance model, for example, and we're getting the summary of those results. And actually what we end up with when we do that is the same results, just using a different function. So we're getting an F value of about 6.558 and a P value of about 0.00345. And then finally, just to close off, in this final function, what's happening here is a linear model's being fitted basically across that data that we're using, and then we're using the ANOVA, the inbuilt analysis of variance function, in order to obtain the results. So you can have a look here at the ANOVA function, which computes the analysis of variance or deviance for one or more fitted model objects. And when we do that, we end up with, again, another another f value of 6.55, another p-value of 0.0034. So I hope that that's reasonably clear and that you've had the opportunity now to kind of see how we calculate that at each step. So essentially, if that's still not clear to you, then what you need to do is you need to read the book and look at how these calculations take place on a step-by-step approach. You need to go back to the 6 different calculations which I listed within the lecture notes, and make sure that you're able to basically generate each one of these input variables here from the data that we got in this example, and then work through the calculations so that you're able to understand essentially what's going on at each step within the calculation. And then hopefully you'll be able to obtain the desired f-stat that allows you then to evaluate the data being tested.